Greetings for the day, dear students. Today I will discuss a new topic, that is biopolymer interactions, and today I will cover the interactions of water. Now, what are water interactions? These are weak interactions in aqueous systems. For example, we can see the hydrogen bonding in ice. Internal cohesion of water. What is internal cohesion of water? Water has a higher melting point, boiling point, and heat of vaporization than most other common solvents, as we can see in this table. These properties result from the strong attractions that occur between water molecules in liquid and solid, that is ice states. Here in this table I have shown melting point, boiling point, and heat of vaporization of some common solvents. Now we will see the structure of water molecules. Water is a polar solvent, as we know. Water molecules are polar because hydrogen and oxygen atoms have substantially different electronegativities, that is, affinities for electrons. Because electrons are shared unequally, the OH covalent bonds are dipolar and partial positive and negative charges occur on hydrogen and oxygen atoms, as we can see in the diagram on the right hand side. Here we can see the positive charge on hydrogen atoms and the negative charge on oxygen atom. This feature plus the fact that two unshared pairs of electrons are located within the sp3 orbitals of oxygen atoms creates a net dipole moment in the molecule of water. Now we will see the hydrogen bonding between water molecules. Hydrogen bonds are non-covalent interactions occurring between hydrogen atom of a dipolar molecule such as water and the unshared electron pair of another atom, that is oxygen or nitrogen. These bonds represent the primary way in which water molecules interact with themselves, as we can see in the figure on the right hand side of this slide. And many types of other biomolecules. The strength of hydrogen bonds is of the same order of magnitude as the thermal energy of an aqueous solution, that is the kinetic energy of motion of the individual molecules. Thus, hydrogen bonds are relatively short-lived, lifetime being equal to 1 to 20 picoseconds. The term flickering clusters is used to describe the short-lived group of water molecules interlinked by hydrogen bonds in liquid water. Here in this diagram we can see the angle is 104.5 degree, hydrogen bond is approximately 0.177 nanometer and the covalent bond is 0.0965 nanometer. Now we will see the hydrogen bonding in ice. Each water molecule in ice forms 4 hydrogen bonds to its neighbors, creating a regular tetrahedral crystal lattice, as we can see in the diagram. In liquid water, each water molecule forms hydrogen bonds with the average of 3.4 other water molecules. Due to more expanded crystal lattice structure of ice is less dense than the liquid water and ice floats on water. Hydrogen bonds account for the relatively high melting point of ice and boiling point of liquid water. Now we will see the hydrogen bonding in other molecules. Water molecules are not the only molecules that form hydrogen bonds. In fact, hydrogen bonds readily form between the electronegative atom, the hydrogen acceptor, usually oxygen or nitrogen, and a hydrogen atom covalently bonded to another electronegative atom, the hydrogen donor, in the same or the another molecule, as I have shown in this figure below. Because carbon has about the same electronegativity as hydrogen, hydrogen atoms covalently bonded to carbon atoms do not participate in hydrogen bonding. Here in this diagram we can see the hydrogen acceptor and the hydrogen donor. Hydrogen bonding in other molecules, we will see some other examples. Alcohols, aldehydes, ketones and compounds containing NH bonds all form hydrogen bonds with water molecule and tend to be soluble in water as shown in the diagram. Molecules such as sugars, amino acids which contain these functional groups commonly are quite soluble in water because of the stabilizing effect the hydrogen bonds have on the interactions between the solvent and solute. Biologically important hydrogen bonds between Watson and Crick 80 base pairs are shown in the figure on the next page. Hydrogen bond directionality and the strength. Hydrogen bonds are highly directional in the strength, and that depends on the proper alignment of the interactions. As we can see in the diagram, the best alignment occurs when the orbital containing the unshared electron pair of the acceptor atom is in line with the covalent bond between the donor atom of the hydrogen. Directionality confers bonding specificity as with the Watson-Crick hydrogen bonds between the bases of double helical DNA, that is A, T, G and C. That result in very precise three-dimensional structure for nucleic acids and protein molecules. Classification of biomolecules based on their interactions with water. Polar biomolecules that dissolve easily in water are referred as hydrophilic, that is water loving molecules, and non-polar biomolecules that do not dissolve appreciably in water are called hydrophobic, that is water fearing molecules. Amphipathic biomolecules have significant amount of both hydrophilic and hydrophobic structures. Like hydrophobic biomolecules, they tend to associate when placed in contact with water molecules. Examples of these three classes of biomolecules are shown in this table. Now we'll see the ionic interactions of water. Ionic interactions occur between cations and anions. These bonds are non-directional and strength depends on the distance of separation, that is represented by small r according to 1 by r square. The strength also depends on medium, that is the dielectric constant of the medium, and it is less in polar than non-polar solvents. Water is effective and at screening the electrostatic interactions between dissolved ions because it has a high dielectric constant, a physical property that reflects number of dipoles in a solvent. The dielectric constant of water is 78.5, whereas the dielectric constant of benzene for example is 4.6. Now we will see solvation of crystalline substances by water. Ionic compounds such as sodium chloride are readily dissolved in water, as we can see in the diagram. Water molecules hydrate and stabilize sodium ions and chloride ions, weakening the electrostatic interactions between them and countering their tendency to associate in a crystalline lattice. The resulting increase in entropy, that is the randomness of the system, is largely responsible for the ease of dissolving NaCl in water. Solvation spheres of water molecules surround ions in solutions. Water molecules orients so that the negative ends of the dipoles contact the cations and the positive ends contact anions in solution. Interactions of hydrophobic molecules with water. Hydrophobic molecules such as hexane and the non-polar portions of the amphiphiles such as long chain fatty acids lack polar functional groups that can interact with water molecules. This results in the highly ordered cage-like shell, that is clathrate of water molecules immediately surrounding the non-polar molecules, as we can see in the diagram. Suspension of a hydrophobic substance in water is thermodynamically unfavorable due to the decreased entropy of water molecules in the cage-like shell. The hydrophobic effect. The hydrophobic effect and the term hydrophobic interactions refers to the entropy driven aggregation of non-polar molecules in aqueous solution that occurs to minimize the ordering of water molecules with which they are in contact. This is not an attractive force but rather a thermodynamically driven process. The amphiphiles such as detergent molecules or long chain fatty acids form molecular assemblies which are known as micelles, wherein the hydrophilic portions of the molecules are in contact with water and hydrophobic regions are sequestered away from water in the interior of the assembly. The hydrophobic effect drives the formation of membranes and contributes to the folding of the protein and the formation of double helical DNA. Now we will see the molecular interactions displace bound water molecules. A somewhat ordered layer of water molecules occur around the solutes, even polar ones in liquid water. In enzyme substrate interactions, ordered water molecules are displaced due to binding, as we can see in the figure. The entropically favorable release of the water molecules provides thermodynamic push towards the formation of enzyme substrate complex. Now we'll see the van der Waals interactions. Van der Waals interactions are bonds between fluctuating induced dipoles within the electron clouds and interacting molecules. These bonds can occur between non-polar or polar molecules. Van der Waals bonds are extremely dependent on the distance of separation between molecules and are significant only when the electron clouds of the molecules are just touching. Values of van der Waals radii and covalent radii of some common elements are shown in the table for reference purpose. In the space filling molecules, models shown throughout the Leininger textbook, atoms are depicted in sizes proportional to their van der Waals radii. Now, non-covalent interactions of macromolecular structure. As summarized above, the non-covalent interactions are weak electrical bonds between molecules. The types of non-covalent interactions are number 1 hydrogen bonds, number 2 ionic, that is electrostatic bonds, number 3 are van der Waals interactions. The non-covalent interactions, that is 1 to 5 kilocalories per mole, are typically 100-fold weaker than the covalent bonds. Their stability is only slightly greater than thermal energy in biological systems. Nonetheless, non-covalent interactions play important roles in proteins and nucleic acids stabilization because they are collectively strong. We should note that the hydrophobic effect drives molecular interactions but is not a non-covalent bond per se. Binding water molecules to proteins. Structure analysis indicate that some water molecules are highly bound to proteins. This is illustrated for hemoglobin in the as shown in the diagram, and These water molecules have different properties from those of the bulk water of the solvent. In certain proteins, tightly bound water molecules play roles in catalysis and roles in ligand binding. Now we'll see the colligative properties of water. Solutes alter the vapor pressure, boiling point, melting point, and osmotic pressure of the aqueous solutions. That is the colligative properties of water. In all cases, these physical properties change due to the fact that the concentration of water is lower in solution than it is in pure water. The effect of solute concentration on colligative properties of water is independent of the chemical properties of solute and depends only on the number of solute components dissolved in the sample of water. Now we'll see movement of water across plasma membranes. Osmosis is the movement of water across a semi-permeable membrane in presence of osmotic pressure difference across the membrane. We all know this. Most isolated cells have a high concentration of dissolved solutes within their cytoplasm. Thus, they are prone to damage the water uptake induced the cell lysis. The terms isotonic, hypertonic and hypotonic refer to the relative concentration of solutes in cell's cytoplasm and the concentration of solutes in the water in which the cell is suspended, as shown in the figure. Water will always move towards the side of the membrane with higher solute concentration. So this was all about the water interactions. Thank you. Have a nice day.